Hello everyone and welcome to section 7.7, base E and natural logarithms. So far we've seen logs with various bases, 2, 3, 5, whatever, and we know that our common base is 10. We also have what's called the natural base, and there's this number that's an irrational number that is approximately 2.71828, blah blah blah. That exact value is definitely not important, but it is used to model continuous growth and continuous decay. So some things don't gain interest, every quarter or every year. Some things like bacteria will continuously grow in number. So this kind of helps model things like that more. We will see this as ln of x, for which we will simply say natural log of x. Ln comes from the Latin form of saying natural log, so that's kind of where that comes from, but it is natural log. Don't say ln, some teachers, it'll definitely drive them nuts. So, since this is just a different base, all of our rules that we've seen so far still exist. So if I was going to write an equivalent logarithmic equation for e to the x equals 23, well, instead of writing log, I'm going to write ln, or natural log. My base is e, that's taken care of already by the natural log. My argument equals my exponent. Same as we did with logs. It looks different because, well, we no longer have log, we have natural log, but the process is still the same. This is still your base, this is still your argument, and that's still your exponent. So if I was going to write an equivalent logarithmic equation for e to the fourth equals x, my base is e, so I've got natural log of x equals my exponent of 4. If I was going to go the reverse direction and write natural log of x is approximately 1.2582, I would write, I've got a base of e to the exponent, and then since there's an approximately, I'll just keep with the approximately. So it's approximately x. Similarly for the next one, natural log of 25 equals x. I've got a base of e to my x equals 25. Same rules as logs, it's just natural logs. So we have those same properties of logs. They apply for natural logs as well. So I know that numbers out in front become an exponent. Addition turns into multiplication. So I've got natural log of 3 to the fourth times 6. 3 to the fourth times 6 is 486. So I've got natural log of 486. Now if I want to check this on my calculator, I very well could. So if I was just typing in 4, natural log button is pretty much right next to the 4, and it automatically gets your parentheses for you. I just want the natural log of 3, close my parentheses, plus natural log of 6. I get a value. Check that against the natural log of 486, and we have the same value. So that's where our natural log button is. We've already seen log. There are 2 buttons for e. Sometimes one will be more useful than the other. We have second natural log, gets you the e to the exponent right away, and then if with the old OS it will open that parenthesis for you. Otherwise, if I hit second division, I can just get a plain old e if I don't want to take it to a particular exponent. For example, if I want to see the value, I've got it right there. A lot of times, though, the second natural log might be more useful. Alright, solving. Similar to what we did before, I want to try to get e all by itself. Then I'll use my strategies. So, first off, I will subtract 4 on both sides. So I've got 3e to the negative 2x equals 6. Goal is to get e all by itself, so I'm going to divide both sides by 3. So I've got e to the negative 2x equals 2. Now, I want to find out what x is. E is an actual number. E I can work with. In order to get my exponent down and out of the exponent, I need to take the log of both sides with the same base. If I want the log base of e to kind of cancel out that log e, I'm going to use the natural log. So I'm going to take the natural log on both sides. My exponent comes out in front. So before anything cancels out, I have negative 2x, natural log of e, equals natural log of 2. Since natural log is already base of e, I'm essentially asking myself, hey, what power of e gets me e? And since that's 1, natural log of e cancels out. I have negative 2x equals natural log of 2. To get x by itself, I'm going to divide both sides by negative 2. X equals whatever we get with that. So I'm going to punch in natural log of 2, close my parenthesis, divide by negative 2, and I get an answer. To the nearest 10,000th, we've got negative 0.3466, since that 7 rounds up that 5. Similar strategies to what we did with logs, it's just we've got an e that we've got to worry about. It would be the same thing as if that was, say, a 5. We would do the same exact thing, except we would take the log base 5 of both sides. Natural log is just easier because our calculator will do it for us. Solve the inequality. Same rules as before, where when we rewrote, our x stayed on our left. So I'm going to rewrite. I've got base of e here, remember, so I've got e to the 8th on my right-hand side. And I've just got my argument on the other. Well, if I've got something squared, in order to get that more by itself, I can take the square root of both sides. E is a number, but instead of finding out what e to the 8th is and then taking the square root, we can sort of treat it like a variable as it is handy to us. Remember, we divide the exponent by 2 when we're taking the square root. So, get x all by itself. And we'll divide by 3. And let's figure out what that is with our calculator. So I've got e to the 4th, and I'm going to use that second natural log button, just because I already want an exponent, minus 1. I'm going to hit enter, and then divide by 3. So that way I actually get my answer. Other option would have been to put my e to the 4th minus 1 in parentheses, just so I make sure I'm following the order of operations. Because otherwise, if you just typed it straight through without any parentheses, your calculator will do exactly what you're asking it to, and do the exponent, take 1 divided by 3, and then subtract, which is not what we want. And we see we have the same thing. So x is greater than 17.8661. Lots of calculator stuff with this section. So, as we talked about at the very beginning, this is modeling things growing or decaying continuously. It is possible for money, for example, to be compounded continuously. So we have a formula which many mathematicians just nickname PERT. It's our principal times e to the rate times time. Or if you wrote it all out, PERT. So, a couple different situations that can happen with this. Remember that your rate, of course, has to be as a decimal. So, it all depends on what we might possibly be solving for. So say we are solving for the balance after a certain amount of time. We're looking for A. When we know we deposited $700, we are getting 3%, and we're waiting for 8 years. So just type it straight in. And we get $889.87. Remember, with money, we do want to round to 2 decimal points. Not too bad for letting money sit. Now say you were saving for something, and you were in an account that gave you interest continuously, and you wanted to get to $1,200, and you wanted to know how long it would take you to reach that point. So, set up what we know. We want to reach at least $1,200. So, I'm going to put that on the right-hand side just because I know that my quantity has to be greater than or equal to that 1,200. So, I've got 700 times e to the 0.03 times t. I want to get that t all by itself. So first thing we can do is isolate that e. Next thing we do is, since I want to get that t, which is presently in the exponent, I've got to take the natural log of both sides, and remember the natural log of e cancels out, or rather simplifies to 1, and my exponent goes out in front. Now to get t by itself, I'm just going to divide by 0.03. So, if I take the natural log of 12 divided by 7, and then divide that by 0.03, I get 17.97 years. If you wanted to know exactly, it would be at that point you would take that decimal piece and multiply by the number of days in a year, so at about 18 years. If you wanted to check, you can always plug back in and double check that you are greater than or equal to 1,200 there. Last possible scenario. You want to reach a balance of $1,500 after 12 years, and you're not quite sure how much to deposit. So, we want to reach $1,500. Don't know how much to deposit. So, though this seems complicated, since e is a number, I've essentially got something like 2x, where 2 is kind of like this. It's just some sort of number times an unknown variable. So I can just divide both sides by my power of e. So if I took 1,500 divided by e to the 0.03 times 12, the amount I would have to invest is $1,046.51. That's pretty much it. I'll see you in class.